Hi everyone, my name is Seth Logan and I'm a coastal engineer with SJL Engineering. Along with my colleague Pete Zuzek from Zuzek Inc, whom you'll be hearing from a bit later in this presentation, I wanted to thank you for joining us today to learn about the Shoreline Natural Hazard Mapping Update for Essex County. This work is being completed by a technical team that's comprised of Zuzek Inc, SJL Engineering, and DHI. The purpose of this presentation is to give you an overview of shoreline natural hazards and how they're mapped for Canadian Great Lakes coastlines through the lens of a changing climate. And the first section of the presentation is going to focus on climate change projections, particularly climate change projections with impacts on coastal communities, with the second part of the presentation focusing on the three natural hazards that are mapped for Ontario shorelines. The first of these is the flooding hazard. Then I'll turn it over to Pete Zuzek to discuss how the erosion hazard and finally the dynamic beach hazards are mapped. So these three natural hazards are defined in the provincial policy statement, which is issued under the Planning Act, the most recent of which was in 2020, pictured here on the right. Also in that document is section 3.1.3, which reads that planning authorities shall prepare for the impacts of a changing climate that may increase the risk associated with natural hazards. And that statement has actually been a part of the provincial policy on natural hazards going back a long time, all the way to 2014, in the 2014 provincial policy statement. So although it hasn't necessarily been adhered to in the past, adopting climate change projections in our natural hazard mapping is really nothing new as it relates to provincial policy. With that in mind, the first section of this presentation is meant to set the stage by providing some background information on climate change as it relates to the Great Lakes and its projected impacts on coastal communities. First, and no real surprise here, our climate is warming. The top image on the left shows how much average winter temperatures increased between 1948 and 2016 across Canada. In Ontario, we've experienced warming that is similar to the global average of roughly 1 degree, but as you can see from this map, there are parts of Canada where warming has been much more pronounced. The bottom left image here shows a similar map, but this time with projected changes to the end of this century, assuming a fairly severe global emission scenario, which is known as RCP 8.5. And in this scenario, Southern Ontario is projected to experience winters that are 5 to 7 degrees warmer relative to the pre-industrial period. Now looking at the graphic on the right, not surprisingly, this warming translates to an overall increase in projected water temperature for the Great Lakes. So why is that important, or what is the key outcome of having warmer lakes, or one of the key outcomes? It's that we have less lake ice during the winter months. And this is a trend that we've already seen all over the Great Lakes. This chart on the right shows the number of days on the y-axis here, with at least 10% ice concentration at 4 locations offshore of the Pelee Peninsula on Lake Erie, which you can see here on the map on the left. The left half of this chart over here is the decade from 1977 to 1986. The right half over here is the most recent decade of analyzed data from 2012 to 2021. And from this plot, you can see that while the 70s and 80s saw somewhere in the neighborhood of 50 to 80 ice days in a typical winter at these 4 locations, the most recent decade in this plot, especially if you ignore 2014 and 2015, which were polar vortex years, the rest of that decade featured an average of somewhere around 30 ice days. Now that's just 4 locations on Lake Erie, but we've looked at this all over the Great Lakes and found very similar results everywhere. And why is this important? Well, it's important because ice provides protection to our shorelines against wave energy and storms during the winter months. Ice-free winters therefore result in a much greater amount of wave energy impacting our shorelines throughout the year, which leads to higher rates of erosion. In a recent modeling study where wave generation was simulated over Lake Erie for a 14-year period, first with the historical ice cover included, and then again with all of the ice removed, it was found that the amount of energy impacting the shoreline in the western basin of Lake Erie, for example, as you can see here in this figure, increased by 120% in the winter months. Another important way in which climate change is projected to impact the Great Lakes is through its influence on water levels. Water levels on the lakes are primarily a function of water supply. So these comes from, for the most part, precipitation and snowmelt. And historically, lake levels rise and fall with wet and dry periods. These periods are clearly evident from a plot of historical monthly mean lake levels, such as the plot in the top right corner of this slide, which shows the Lake Erie water levels over the last 100 years or so. Where climate change comes into play is that research tells us that variability in water supply is likely to increase in the future, meaning higher highs and lower lows than we've experienced in the past. This is shown in the bottom right plot down here, which provides lake level projections for 4 different increases in global mean temperature, 1.5, 2, 2.5, and 3 degrees Celsius, compared to the historical measured period. In other words, we are likely to experience future wet periods that result in lake levels even higher than we saw in 2019 and 2020 for Lake Erie and Lake St. Clair. So this gives you an idea of the type of information that needs to be accounted for when mapping shoreline natural hazards in Ontario in order to be compliant with the provincial policy statement for the inclusion of climate change projections. Now I'm going to move into the second part of the presentation, which is a few slides on the flooding hazard. So flooding, which is the first of 3 hazards that we're going to talk about today, is something that is at the forefront of lots of people's minds in this part of the province after 2019 and 2020. The photos that you see here were taken during that period on the east side of the Pelee Peninsula. The flooding hazard, as defined by provincial policy and provincial technical guidelines, is shown graphically here in this figure. It's a combination of 2 things. The first is the 100-year flood level over here, and the second is an allowance for wave uprush, or the effects that waves have on the shoreline. The 100-year flood level is the total water level that has a 1% chance of occurring in any given year, and it's the result of 2 things occurring in combination. The first is the static lake level, or the lake level resulting from the total amount of water in the lake. And the second is storm surge. Storm surge is the temporary, localized increase in water level that you get in certain parts of the lake due to strong wind events blowing across the lake and pushing water in one direction. You'll note that on this graphic there's also an optional 15-meter allowance at the end here that gets added to the flooding hazard in Ontario to form the full regulated shoreline area. So what are the steps for evaluating the flooding hazard at a given location? Well, for locations around the Great Lakes where we have long-term water level gauges, it's generally a 4-step process. First, we have to do a statistical analysis of static lake levels. And for this study, we've done this 4 different times for 4 different scenarios. The first being based on 100 plus years of historical data. Scenario B being based on climate change lake level projections for a mid-century moderate global emission trajectory. Scenario C being the same global emissions trajectory but for a late century water level projection. And finally, scenario D, or the final scenario, being a late century projection using a much higher or more severe global emission trajectory. All of those climate change projections come from the Environment and Climate Change Canada study, which is pictured on the right in this slide. And this is really the latest and greatest research into climate change impacts on the Great Lakes. Once we've analyzed static lake levels, then we do a statistical analysis of storm surge magnitudes based on the historical measured storm surge events at the water level gauges. Then we do what's called a joint probability analysis of these 2 things, storm surge and static lake levels, meaning what is the probability of a given total water level being reached by a combination of the 2 processes. And ultimately that gives us the 100-year flood level. Finally, the last step is through a combination of statistical analysis of waves and wave modeling along the shorelines, we can estimate the wave uprush extent, which is the final piece of the flooding hazard. In this slide, you see the assessed 100-year flood level from the study for the historical scenario and all three climate change scenarios at each of the water level gauges within Essex County. So these gauges are at Bell River on Lake St. Clair and Bar Point and Kingsville on Lake Erie. Now, this is all well and good, understanding 100-year flood levels at the water level gauge locations, but we also need to know what the levels are in between these locations. So to assess that, we do hydrodynamic modeling of storm surge events. And that's because the static lake level component is consistent across the lakes, but the storm surge component of the 100-year flood level is variable depending on where you are along the shoreline. So our partners at DHI led this work and ran a wide variety of storm surge events on both Lake St. Clair and Lake Erie, as well as through the Detroit River, using a high resolution numerical model, which you can see an image of in the top left. The top right graphic on this slide is a time series of modeled water levels versus measured water levels through a major storm surge event measured at Bar Point. The peak of that event would be right here, and you can see from this plot the overall accuracy of the model when compared to real measured data. The bottom right plot shows the wind direction as the little black arrows and the storm surge magnitude as the color contours in this plot at the peak of one of the major storm surge events simulated in the western basin and the western side of Lake St. Clair. The last step in the overall assessment of the flooding hazard is to evaluate wave uprush, which is shown graphically in the image in the top right of this slide. And to do this, our partners at DHI once again set up a detailed wave model for both Lake St. Clair and Lake Erie, which you can see in the top left and bottom left of this slide, respectively. We then used extreme wave outputs along the shoreline during major wave events to predict the extent of wave uprush all along the shoreline, accounting for local topography. We did this at something like 130 discrete locations around the Essex County coastline. The final product from all of this information and analyses is a flooding hazard line or a flooding hazard polygon on a map, or in this case, 143 maps for Essex County. And this flood hazard line or polygon depicts the areas that are susceptible to flooding at the 100-year or the regulatory level under both historical and climate change conditions. And this is an example of one such map, still in draft form, which depicts the extent of the flooding hazard for a portion of the Lake St. Clair shoreline just west of Bell River. The light blue shading on this map is the flooding hazard based on historical conditions, whereas the darker blue shading, which is a little bit further landward, is the flooding hazard based on the mid-century climate change scenario. Now I'm going to pass the presentation off to Pete Zuzek, and he'll take you through the other two regulatory shoreline hazards, which are the erosion and the dynamic beach hazards.
Thanks, Seth. My name is Pete Zuzek, and I'm going to speak to you today about mapping of the erosion hazard. The provincial methodology to map the erosion hazard includes two components to produce a horizontal setback from the water line. The first is the allowance for erosion over a 100-year planning horizon, including the impacts of climate change. This is measured from the water line inland. The second component of the horizontal setback is a stable slope allowance, shown graphically here at the bottom. There is an option to include an additional 15-meter allowance to define the regulated area. The shoreline of Essex County has been subdivided into 27 different reaches or segments of shoreline that feature similar characteristics. And then within each of these segments, we establish a long-term recession rate. The next map highlights some shoreline change measurements from 1947 to 2022. In the top left, we have the position of the water's edge in 1947 compared to that 2022 image in the background, and we see that the long-term recession rate on average is 0.4 meters per year. Further to the east in the graphic, we have a rate that's even higher at 0.56 meters per year on average. Erosion rates are also calculated for high bluff sites to map hazardous lands. such as the example in the lower left, where you can see a high, actively eroding bluff. This type of mapping helps landowners make safe development decisions. The building highlighted in the red dashed circle is a structure that was built too close to the bluff without a permit, and one that would certainly not last a 100-year planning horizon. The next map shows you some of the hazard mapping generated on the south shore of Lake Erie. The green arrow is pointing to a green line for the inland extent of the erosion hazard limit. This is the setback required for future development decisions along the eroding shoreline. The blue shaded area is the flood hazard limit that Seth described earlier in the presentation. Part 4 of the presentation is the mapping of the dynamic beach hazard. And as we can see in the photographs, beaches are highly dynamic. They change in shape, in height, in width, in response to storm events and other factors. In the photograph on the left, the Hillman Marsh barrier can be seen as almost completely inundated during a storm event. And then in our calm conditions, we have a wide beach fronting the barrier system. As I mentioned, beaches are highly dynamic in the Great Lakes region, and protecting them with the mapping allows these dynamic processes to continue. In the schematic diagram on the left, panel 1 shows you a beach and dune system with some nearshore sandbars under average calm lake conditions. If we forward to the second panel, we can see that the beach is quickly inundated during periods of high lake levels that can last months to several years. During storm events at these higher lake levels, waves are able to propagate over the sandbars and erode material from the beach and the dune and transport that into the nearshore environment, storing it in the sandbars. When lower lake levels return, these sandbars then release their sediment, is pushed back on shore, and the beaches can recover and the dunes can reflate and start to grow again. And so this process, the cycle, can happen naturally when beaches are protected and not developed. We have an example here of a very dynamic barrier beach system on the east side of the Pelee Peninsula, the Hillman Marsh Barrier Beach, and we see a photo of it here in 2016. And following the period of record high lake levels in 2019, this barrier beach breached and is now has a gap in it on the order of 500 meters, just highlighting how dynamic and sensitive these barrier systems are to high lake levels, storm events, and sediment supply. The provincial methodology to calculate the dynamic beach hazard limit includes several components, as shown in the diagram below. The first is the 100-year flood level, calculated as the water level that has a 1% chance of occurring in any given year and includes the impacts of climate change. The second component of this horizontal setback is an allowance for wave effects, for waves to rush up the profile and cause additional flooding inland. The third is a dynamic beach allowance, shown here as the standard of 30 meters. Like the other setbacks, the possibility to add a 15-meter allowance to further define the regulated area. The mapping is ongoing for the dynamic beaches in Essex County, Lake St. Clair and Lake Erie. A couple examples of areas where we anticipate the beaches to be classified as dynamic include the fillet beaches of Bell River on the left, the Cedar Beach fillet beaches adjacent to the navigation channel in the center photograph, and the Seacliff Beach in Leamington. Thank you for listening and watching our presentation on shoreline natural hazard mapping in Essex County. If you have any questions, don't hesitate to speak to some of the individuals at the open house, and they'd be more than happy to answer your questions.